Hello class and welcome back. In our last session, we really got our hands dirty building that foundational engine, the single head of self-attention. Today, in part 4, we're going to see how we take that one elegant component and scale it up, way up, into the colossal structures that power modern AI. All right, let's get started. So here's our plan for today. First, we'll look at why just one passive attention simply doesn't cut it. Then we'll see how the architecture scales sideways with multiple heads, how it adds a kind of knowledge store with MLPs, and finally, how it scales upwards by stacking layers. By the time we're done, we'll have the complete blueprint. Now, as we've already established, self-attention lets every single token in a sentence talk to every other token. It's a way for them to share information, to update their own meaning based on the full context. You can kind of think of it as a single really focused conversation happening all at once between all the words. Well, the answer, as you've probably already guessed, is resounding no. See, a single pass, a single conversation, can only really focus on one type of relationship at a time. And language, well, language is layered, it's full of nuance. It's just far, far more complex than that. So the first, and frankly, most ingenious solution to this problem is to say, okay, let's not have just one conversation, let's have many different conversations all happening at the exact same time, in parallel. This beautifully simple idea is called multi-headed attention. And this really shows you the kind of scale we're dealing with. We're not just talking about doubling or tripling the mechanism. No, a single attention block in one of these large models can have 100 or even more of these parallel attention mechanisms, each one doing its own thing. And the key here, the really important part, is that they're independent. Every single one of those 100 heads gets its own unique learnable set of query, key, and value matrices. This means each head can become a specialist, learning to hunt for a completely different kind of pattern or relationship in the text. So just imagine, you could have one head that's totally focused on grammar, figuring out which adjectives are describing which nouns. At the very same moment, another head could be working to figure out what a pronoun like it refers to from maybe 5 sentences back. A third might be tracking concepts, connecting king and queen, while the fourth is following the action, linking verbs to their objects. All of it happening at once. Okay, so after all these parallel conversations have happened, and the tokens are enriched with all this new context, the model needs another piece of the puzzle. It needs a way to actually process that information. And this is crucial to access general knowledge about the world. This is where the model's knowledge store comes into play. Now, this slide, I think, shows a really clear division of labor. Think of it like this. Multi-headed attention is for communication between the words. It's the group discussion. The MLP, the multi-layer perceptron, is for the individual thinking that happens for each word after it's heard what all the other words had to say. This right here, this is the model's library. So if you give it a phrase like Michael Jordan plays, the fact that the most likely answer is basketball, that knowledge isn't in the input text anywhere. That's a general fact about the world, and it's stored deep inside the parameters of these MLP layers. So we now have our two fundamental building blocks, the multi-headed attention block for sharing context, and an MLP block for accessing knowledge. The final trick for scaling this whole thing up is wonderfully simple, but incredibly powerful. We just repeat it, over and over again. These two operations, the group discussion and the individual thinking, are bundled together into a single standard unit. We call this a transformer block. The output from the attention part is fed directly into the MLP part. Simple as that. And right here, this is the magic of deep learning. The updated vectors that come out of one complete transformer block become the input for the very next block. So with each layer that the information passes through, the representations become richer, more abstract, and just more deeply understood. And that is the crucial point. This is what makes deep learning so deep. It's this huge stack of repeated processing blocks. A model like GPT-3 doesn't just do this once or twice. It stacks 96 of these layers, one right on top of the other, creating this unbelievably deep pathway for information to flow through. All right, so we've basically built our skyscraper. It's got a wide base of all those parallel attention heads, and it's stacked up into a deep tower of these repeating transformer blocks. But why? Why has this specific design become so completely dominant in the world of AI today? The answer really comes down to one critical concept from computer science, parallelizability. You see, unlike older models that had to read text one word at a time sequentially, just like we do, the transformer architecture can look at and process everything all at once. This entire design is basically tailor-made for modern hardware, especially GPUs, which are fantastic at doing tons of simple calculations at the same time. By getting rid of that need to process things one by one, it means we can just throw unimaginable amounts of data and computing power at these models. And as it turns out, that ability to scale is really the secret ingredient that unlocks their incredible power. So there we have it, the complete architectural blueprint of a modern large language model. But, a blueprint isn't a building. Right now, we just have this massive, complex, but static structure. The final and maybe most important piece of the puzzle is figuring out how we actually train the hundreds of billions of parameters inside it to learn from data and, to think. And that training process is exactly what we will be covering in the final installment of our series, Part 5.